This is the first video on moment of inertia. The topics covered are moment of inertia, theorem of parallel axis, theorem of perpendicular axis, radius of gyration, and modulus of section. Introduction. Moment of inertia. If a mass m is situated at a distance x from a certain axis, then the product of mass and its distance from the axis is called as first moment of mass. Just like in engineering mechanics or applied mechanics, uh, moment is product of force and perpendicular distance. Here it is taken, force is instead of force the mass is taken, and x is the distance from a certain axis. So m into x is called as first moment of mass. If this first moment of mass is again multiplied by its distance from the axis, means we take its moment again about the same axis, then it is called as second moment of mass. It is given as mx square. This quantity is called as second moment or moment of inertia, and it is written as mi or only I. In engineering practice, the mass is replaced by area. Thus, the moment of inertia is defined as sum of the second moment of areas. Now, suppose here I'm explaining moment of inertia of a plane lamina. Now, this is some lamina whose total area is capital A. In this area, we consider elemental area dA, and its distance from this is the x-axis, from the distance x-axis is y, and for this area dA, its distance from y-axis is this horizontal distance is x. So let us consider a small elemental area dA in a plane lamina of area capital A as shown in figure. The centroid of the area dA is at a perpendicular distance of x and y from the reference axis y and x respectively. Here it is very important to remember that when we consider the y-axis, the distance is horizontal and it is x. And when we consider the horizontal x-axis, the vertical distance is y. So for the distance x is from axis y and distance y is from axis x. By definition of mi of this small area dA about the axis, about x-axis is dA into y square. Now if I want mi of this small elemental area dA about the axis xx, then this area dA will be multiplied by y 2 times. So dA, the area, into y square will be the moment of inertia of this elemental area dA about the axis xx. If the moment of inertia of all such small areas are added together, then the mi of entire area A is obtained. If I divide this full area into small elemental areas dA here, here, here again at all the places, and I take the moment of inertia of all such elemental areas and do the addition of it, then this summation dA y square is the mi of the full area about the axis xx. Similarly, if I want mi of full area A about y-axis, then this Iyy will be equal to summation of all the elemental areas dA into x square. This is the basic for moment of inertia. Now let us come to theorem of parallel axis or parallel axis theorem. Now this is some lamina of area A. Total area of this lamina is A. This is the centroidal axis XX. This is axis AB, which is parallel to the centroidal axis XX. The distance between these two parallel axes XX and AB is H. I have underlined H with some purpose, which I'll be explaining in my next PPTs. So this distance is between axis XX and AB is H. The statement is like this. It states that mi of a plane lamina about any coplanar axis parallel to the centroidal axis of lamina is summation of mi of lamina about its centroidal axis and the product of area of lamina and square of distance between the two parallel axes. So the IAB, if I want the moment of inertia about any axis which is parallel to centroidal axis and say it is axis AB, IAB, then it will be equal to IXX, that is the moment of inertia about the centroidal axis, IXX plus area, this is the total area of the lamina, A, and H square, where H is the distance between the axis XX and axis AB. So where AB is equal to moment of inertia of area A about axis AB, IXX is moment of inertia of area A about axis XX, A is full area of the plane lamina, and this H is equal to the distance between the two parallel axes AB and XX. If those who are in little poor in English and this word plane lamina comes again, so here it is another definition for parallel axis theorem, which is maybe few students will find it little easy. It states that mi of any axis parallel to the centroidal axis is equal to the mi of the area about its centroidal axis plus the product of area and square of distance between the two parallel axes. So here what is important is AB is parallel to the centroidal axis XX, then IAB is equal to IXX plus AH square, where this H is distance between the axis AB and XX. This is the parallel axis theorem which we'll be using while solving the problem. Theorem of perpendicular axis or perpendicular axis theorem. It states that if IXX and IYY be the moment of inertia of a plane lamina about two perpendicular axes meeting at O, then the moment of inertia about the axis ZZ perpendicular to the plane and passing through intersection of axes XX and YY is given by IZZ is equal to IXX plus IYY. Now here this is a lamina, again plane lamina, and this is the point O, and from here is the centroidal axis. This is the axis X and this is the axis Y. X and Y axis, they are in the lamina, and Z is perpendicular to this plane. Z is also called as polar axis, or it is a Z axis, and if I want about this axis ZZ moment of inertia, then it is given by IZZ is equal to IXX plus IYY. All these three axes XX, YY and ZZ are perpendicular to each other, and this is known as perpendicular axis theorem. IZZ is sometimes called as polar moment of inertia, and it is denoted as IP as shown here. The polar moment of inertia is defined as inertia of a plane area about an axis perpendicular to the plane of the figure with respect to the points where the axes X and Y intersects the plane. So this is the definition of polar moment of inertia. Let us come to the next concept in moment of inertia, that is radius of gyration. If the plane lamina of area A is divided into smaller areas like dA1, dA2, dA3, etc., and they are arranged or placed at equal distance from the axis AB along the line MM without altering the MI of the plane lamina about AB. Then the perpendicular distance between the line MN and axis AB is called as radius of gyration of the lamina about axis AB. Here what we do is, this is the total area A. It is divided into small areas dA1, dA2. So these are the elemental areas dA1, dA2, dA3, dA4 and likewise. So it is divided into n number of elemental areas, and it is placed along the line MN at a distance k from the axis AB in such a way that the moment of inertia of this full area A about the axis AB is the same as the moment of inertia of all these elemental areas taken together about the axis MN. So the moment of inertia of all these elemental areas when taken about AB is same as the moment of inertia of this full lamina A about AB. The moment of inertia does not change. So IAB, moment of inertia of this lamina about axis AB, is equal to now moment of inertia of this all elemental areas. That will be, now for this elemental area, moment of inertia about the axis AB by its basic definition will be dA1 into k square. For this dA2 it will be dA2 into k square plus dA3 into k square and so on. If k square is taken common, in the bracket what remains is dA1 plus dA2 plus dA3 plus dA4 and so on. So what is this dA1 plus dA2 plus dA3 total taken as? It is the full area A, because we have divided this A into dA1 dA2. So if I add all these areas dA1 dA2, I get the full area A. So this is A. So k square A, or I can write it AK square. Now if I want k is equal to, then it will be under root, this is full under root up to here, bracket open, this A when it comes here it becomes divided by, so IAB divided by A full taken in bracket, and if I do under root, IAB upon A will give me k square. If I want k, I have to do under root. So under root bracket open IAB upon A bracket close, this gives me the figure k, which is known as radius of gyration. This k is known as radius of gyration, where IAB is moment of inertia of full area A about axis AB, and A is the full area of the plane lamina. So the radius of gyration is defined as, the radius of gyration of an area about any axis is the distance from the axis at which all elemental areas can be placed without altering the MI of the entire area about the axis. It is denoted by the letter k, small k or small r. And if I want it as kxx is equal to, then it will be under root bracket open Ixx divided by A bracket close. If I want kyy, then it will be equal to under root bracket open Iyy divided by A bracket close. Let us see the next concept in moment of inertia, that is modulus of section or section modulus. It is denoted by Z. It is the quantity obtained by dividing the moment of inertia of a section about CG by the distance of the extreme fiber from the central axis. It is denoted by letter Z. Now if I want ZXX, then it will be equal to Ixx divided by, it is obtained by dividing the moment of inertia of a section about CG by the distance of the extreme fiber from the central axis. Now this is one central axis XX, the extreme fiber is this, and the distance will be, if the total height is D here, then D by 2, the central axis will be at D by 2. So Ixx divided by d by 2 will give me Zxx. Similarly, if the full width here is b, then this centroidal axis yy will be at a distance of b by 2. So if I want zyy, it will be Iyy divided by, now the extreme fiber here, the fiber which is far away from yy is this one. This is the extreme fiber here, or this is the extreme fiber here. So it will be Iyy divided by the distance of extreme fiber will be b by 2. So Iyy divided by b by 2 it will be zyy. This is how we define section modulus, and more we will see when we do the calculations. Now we will see few standard moment of inertia. Moment of inertia of a rectangular section. Moment of inertia about the axis xx, Ixx. Now this is the axis xx. This is a rectangle. The width of the rectangle is b. The depth is d. This is the center here. At a distance d by 2 is y bar, and from here to here is y bar, that is d by 2. This is the centroid, and from this point O, this is the distance b by 2, that is x bar, b by 2. So this horizontal distance from here to here is b by 2. This vertical distance is d by 2. This is the centroid of rectangle, and this is the first rectangular centroidal axis xx. And if I want moment of inertia about this Ixx, it is b d cube by 12. The proof for this equation Ixx is equal to bd cube by 12 is not there. So you have to just remember the formulas directly. If I want the moment of inertia of this vertical straddle axis yy, then this yy is db cube divided by 12. How to remember it? If I want about the horizontal axis, then this horizontal dimension b comes once, and this d vertical dimension will come 3 times and divided by 12. If I want moment of inertia about this yy vertical axis, then this vertical dimension d will be coming first d and only once, and this horizontal dimension is b. This horizontal dimension from here to here is b, and it comes 3 times divided by 12. That gives Iyy. If I want moment of inertia about this axis pq, then IPQ is equal to BD cube by 3. BD cube remains the same. Here, if I want about centroidal, I have to divide by 12. If I want here, I have to divide by 3. BD cube by 3. The proof of this is not expected. It is not in the syllabus. The area of rectangle is B into D. Now, moment of inertia for a hollow rectangular section. If this is a rectangle, the outer dimension of this rectangle is capital BD, and inner hollow is small bd. This is the centroidal axis xx, and this is the centroidal axis yy. If I want moment of inertia about the axis xx, then Ixx is equal to, what we do is we consider the outer rectangle. Its moment of inertia about xx will be capital BD cube by 12. Now this hollow section, this is a cut, small bd, so minus small bd cube by 12. So it is moment of inertia of the outer rectangle minus the moment of inertia of the inner rectangle. If I take out 1 by 12 common, then Ixx becomes capital BD cube minus small bd cube bracket close divided by 12. Similarly for Iyy, the moment of inertia of the outer rectangle will be db cube by 12 minus the moment of inertia of the inner rectangle, that is db small db cube by 12. If 1 by 12 is taken out common, then it becomes Iyy is equal to bracket open capital BD cube minus small db cube bracket close divided by 12. This is the moment of inertia of about the axis yy. So this is the moment of inertia here about the axis xx. This is the moment of inertia about the axis yy, and the area will be capital BD minus small bd. So this is how, using this formula, we will be calculating Ixx and Iyy for a hollow rectangular section. Let us come to the next section. Moment of inertia for a circular section. Now center of the circle is the centroid for circle, and this is the horizontal axis xx, and this is the vertical axis yy. If this is the total diameter d for the circle, then here to here this distance y bar is equal to d by 2. From this point it will be d by 2. The moment of inertia about the x-axis, Ixx is pi d raised to 4 divided by 64. And similarly for a moment of inertia about the y-axis is Iyy is equal to pi d raised to 4 divided by 64. So Ixx and Iyy are equal. The formula is same, pi d raised to 4 by 64. If you substitute a value d raised to 4, then you get Ixx and Yy, they are equal. Now if I want Izz, which will be from this point and perpendicular to the plane, perpendicular to this circle zz, then by perpendicular axis theorem Izz is equal to Ixx plus Iyy, which will be equal to twice Ixx, as Ixx is equal to Iyy. Substitute the value of Ixx, it will be 2 into pi d raised to 4 divided by 64. Now this 2 and 64, when we cancel it, what happens is this will become this 2. If I take this 2 and 32, then it will become 32. 64 will become 32. So pi d raised to 4 divided by 32 will be Ip or Izz. So Izz is also called as polar moment of inertia, Ip. Area of the circle will be pi d square by 4, or pi by 4 d square. So when I want the moment of inertia about xx or yy, it is pi d raised to 4 divided by 64. If I want it about zz axis, then it is pi d raised to 4 divided by 32. Moment of inertia of a hollow circular section. Now this is a hollow circular section. The outer diameter is capital D, the inner diameter is small d. Now if I want moment of inertia about the axis xx, Ixx for the hollow section, it will be moment of inertia of the outer circle, that is pi capital D raised to 4 divided by 64, minus the moment of inertia of the hollow, that is the inner circle, that will be pi small d raised to 4 divided by 64. So this is moment of inertia of outer circle minus moment of inertia of the inner circle. If pi by 64 is taken out common, then it becomes Ixx is equal to pi divided by 64 into bracket open capital D raised to 4 minus small d raised to 4 bracket close. Ixx and Iyy are equal, so Iyy also will be equal to pi divided by 64 into bracket open capital D raised to 4 minus small d raised to 4 bracket close. So this is the moment of inertia for yy, and this is for xx. Now if I want Izz, then by perpendicular axis theorem Izz will be Ixx plus Iyy. Now xx and yy are same, so it will become twice Ixx. If I substitute the value of Ixx, it will be 2 into bracket open pi d raised to 4 capital D raised to 4 divided by 64 minus pi small d raised to 4 divided by 64 bracket close. Here this is 2 and 64. When this I have cancel it, this becomes 32. This is pi d raised to 4 pi capital D raised to 4 divided by 32 minus pi small d raised to 4 divided by 32. When I take this 2 inside the bracket, this is what I get. Now if I take pi by 32 common, then pi divided by 32 into what remains in the bracket is in bracket capital D raised to 4 minus small d raised to 4 bracket close. So this is the formula for Izz. It is same, only thing is here it is pi by 64, here it becomes pi by 32, and bracket open, capital D raised to 4 minus small d raised to 4, bracket close. IZZ is equal to IP, polar moment of inertia. If in the exam polar moment of inertia is asked, then we use the same formula here, which is IZZ. Now area of a hollow circular section will be pi into bracket open capital D square minus small d square, bracket close, divided by 4. Let us come to the next section, moment of inertia for a semicircular section. Now for a semicircular section, this is the base or the diameter AB. This is the axis XX, this is the centroid, and this is the axis YY. Now centroid of a semicircle, this axis XX is at a distance of 4r upon 3 pi from the axis AB, and if this height here will be radius of the circle, that is equal to d by 2. Now if I want moment of inertia about the axis XX, the standard formula is 0.11 r raised to 4. This is the moment of inertia of this horizontal axis which is parallel to this base AB or the diameter. So moment of inertia is 0.11 r raised to 4. If I want about this axis YY, it is pi d raised to 4 divided by 128 in terms of diameter, or it is pi by 8 r raised to 4. So pi r raised to 4 divided by 8. Pi by 8, if we calculate it, comes to 0.393 r raised to 4. In few books you may get this formula, in few books you may get this formula. It is one and the same. The area of semicircle will be pi r square divided by 2. Pi r square is the area of the full circle. If you divide it by 2, we get the area of a semicircle. Here what is very important to remember is, if I want moment of inertia about the axis AB, which is the diameter or the sometimes it's called base, then this IAB is equal to IYY. These YY axis and AB axis have the same moment of inertia. It is pi d raised to 4 divided by 128, or pi r raised to 4 divided by 8, or 0.393 r raised to 4. Now how to remember the formulas? Don't mug up as Ixx is equal to 0.11 r raised to 4. Why? Because suppose if this semicircle I turn it by 90 degree. Now I have turned it by 90 degree. Now my base here, the baseline AB, the diameter was horizontal. Now it has become vertical. Now this is my axis XX here. Now what is Ixx now? Now I cannot write Ixx is equal to 0.11 r raised to 4, because now this has turned. Now this has become, this is the y-axis which is perpendicular to this diameter. Now this is the diameter and this is the axis which is perpendicular to the diameter. So when the axis is perpendicular to the diameter, the moment of inertia, now it will be pi r raised to 4 by 8, or 393 r raised to 4. This will become Ixx here. When I turn it, the axis this turns. So now this is x-axis, but moment of inertia is not 0.11 r raised to 4. This is something very important to remember. Now this is the vertical axis YY here, and now you can see it is parallel to the base. So when this base and this is parallel to the base, so now this is 0.11 r raised to 4. So here IYY becomes 0.11 r raised to 4. It is not 0.393 r raised to 4. So don't mug up that IYY is equal to 0.393 r raised to 4. Remember it as, if the axis is parallel to the diameter, then that axis, for that centroidal axis, moment of inertia is 0.11 r raised to 4. And if the axis is perpendicular to this diameter, then it is 0.393 r raised to 4. So if this is the figure, so to the axis which is parallel here this is the diameter, and the axis which is parallel to the diameter, it is 0.11 r is to 4. Then it may be x or it may be y. It may be horizontal or it may be vertical. If it is parallel to this diameter, then for this centroidal axis, moment of inertia is 0.11 r is to 4, and to the axis which is perpendicular to the diameter. Now this is the diameter here for the semicircle. So the perpendicular to the diameter, the moment of inertia is 0.393 r raised to 4 or pi by 8 r raised to 4. This is how you remember the formulas. Otherwise, if this figure is turned by 90 degree, your formulas will go wrong. Your answer will go wrong. Let us come to the next moment of inertia for a quarter circular section. Now if this is a quarter circular section, the centroid is here. From this center O, it is at 4r upon 3 pi in the vertical direction here, and again this horizontal distance is also 4r upon 3 pi x bar, and this is y bar, and this is the centroidal axis xx here, horizontal axis, and this is the centroidal axis yy here. Here ixx and iyy both are equal, and the answer is 0.055 r raised to 4. For a semicircle, xx and yy are same, and area will be pi r square divided by 4. Now it is only a quarter, so divide by 4. Pi r square divided by 4 will be the area, and xx and yy are equal. Let us come to the next figure, moment of inertia for a triangular section. Moment of inertia, now this is the triangle, base is the width small b, height is, this is h is the height of the triangle. Then this centroidal horizontal axis will be at a distance of h by 3. So this y bar is at a distance of h by 3. Now here about the centroidal axis, the moment of inertia Ixx is equal to bh cube by 36. If I want about this base AB, then this IAB or I base will be equal to bh cube by 12. If I want the moment of inertia about this vertex PQ, now then this moment of inertia about PQ is equal to I vertex is equal to bh cube by 4. How we get it? Now by parallel axis theorem, IAB will be equal to Ixx plus AH square. Now what is Ixx? Ixx is bh cube by 36, where b is this base, h is height of this triangle. So I substitute this value, bh cube by 36 plus area of triangle will be b into h, 1 half b into h, 1 half base into height. So bh divided by 2 into, now this h square, that is h underline, is the distance between the axis AB and XX. This is not this h. That is why I have underlined this. This is height of the triangle is h, and this h by 3 is the distance between the axis XX and AB. So this h underline in this formula will be h divided by 3 bracket square. Now 3 square is 9, and 9 into 2, this is 18, and this h square, this is h bracket square, so this is h square into h, this is h cube. So this is bh cube by 36 plus bh cube by 18. Now for this I multiply and divide by 2, so it becomes 2 bh cube, and 18 into 2 is 36. So 1 by 36 denominator is common. So when I add this, this is 2 bh cube plus 1 bh cube, this becomes 3 bh cube by 36, and 3 divided by 36 is 1 upon 12. So IAB is bh cube by 12, which is we have taken here, and you can directly remember it as moment of inertia of a triangle about the base is bh cube by 36. Similarly, if I apply the parallel axis theorem to this axis PQ, Then IPQ will be Ixx plus A h square. This h is underlined. So now IPQ is equal to Ixx is from here BH cube by 36. Area is B into H divided by 2. Half base into height is the area of the triangle. Now what is this H here? Now H here is distance between the axis PQ and XX. Now distance between this axis PQ and XX will be now H by 3. This is H by 3 and this is total H. H minus H by 3, this will become 2H by 3. So this is the H underline which I have to substitute. So the H underline is 2H by 3. So 2H by 3 is the distance between the axis PQ and XX. So square of it. So what will become? This is divided by 2 and here this is 2 square in the numerator. So this is 4 divided by 2 will be 2 and square of 3 is 9. So this figure will come 2 by 9. This is h square. When I square this bracket, this is h square into h, this is bh cube. So this figure, when I square it and multiply with h by 2, it will become bh cube into 2 divided by 9. Now I multiply here and divide by 4. So 2 into 4 and 9 into 4 will be 36. So this is 36 and this is also 36. This is 8. So this 2 to 4 is 8 and plus 1. This will become 9 bh cube divided by 36. 9 divided by 36 will be 1 by 4. So IPQ is equal to BH cube divided by 4. This is what I have written here. So every time you don't have to do the parallel axis theorem, we can directly remember that about axis AB it is BH cube by 36, about the base it is BH cube by 12, and about the apex it is BH cube by 4. We'll be using directly these formulas to solve the problem. These are the few standard figures and their standard moment of inertia which we'll be using in our next video while solving the problems. Now here is one small assignment given. Define the following terms: moment of inertia, section modulus, and radius of gyration. Question number 2 is state and explain the following theorem: parallel axis theorem, and the second is perpendicular axis theorem. This is the theory which is asked in the exam. Be a master. Thank you.